Hey guys, I wanted to talk briefly about the coronavirus math we see in newspapers and on the internet related to epicalculus AB and what we've studied. There's these types of graphs you can see, you've seen probably. It shows total cases or total deaths, and actually the way it begins here is the same as the way it begins there, and this is typically a logistic function, so gradually the graph we hope is going to curve back down like this. It's a logistic function. This is what the general equation looks like here, and that's what the graph looks like. So we can see that this might be the beginning of a logistic function, and we are really hoping it curves back down soon. And when I say curve down, I mean that it is concave down. A few weeks ago, it seemed to start to happen here on the blue graph somewhere there, that there was suddenly a curve down. It was starting to be concave down, and people were actually pretty happy. The mathematical term we would use for that is that we had reached the point of inflection. Unfortunately, a little bit later, China reassessed how they counted cases, and there was suddenly a big jump in the number of cases. And I want to just mention that this is why mathematics is considered to be easy compared to real life. Students tend to think math is really hard, but in fact it typically ignores difficulty, it typically ignores changes, sudden unexpected events, and real life is much more complex than mathematics. And then now you can see the graph doesn't look like a logistic function anymore because of this change in calculations. The other thing, when you see these graphs, you always have a linear representation, and then you have a logarithmic scale. What does that do? It shows exactly the same numbers, but the vertical scale is different. Here you can see how it's linear. It's 0, plus 20 is 40, plus 20 is 60, plus 20 is 80, plus 20 is 100,000 cases. When you show the logarithmic scale, now every step up is multiplied by 10. So here is 1,000 cases, here's 10,000 cases, here's 100,000 cases, and here's 1,000,000 cases. So why would we be interested in looking at the graph like that, the data like that? Well, because this shape here at the beginning, it's increasing, and we can see that it's increasing faster and faster, as we kind of mentioned earlier, and we want to compare that with exponential growth. Exponential growth appears everywhere. It's a very natural phenomenon when bacteria develops, when populations grow, when money increases. It typically goes with exponential growth, and that's a very fast pace, right? So when we compare it, it's hard to say whether this is the beginning of an exponential function, or is it kind of a parabola, or what kind of growth is it? Is it really fast or not? So by selecting a logarithmic scale, what it does is that if it was exponential growth, then what we would see now in blue would be a straight line. And since what we see is not a straight line, it's concave down, it means that the actual growth is slower than exponential growth. And same here with the logarithmic scale for deaths, we can see that it's not exponential growth because it's not, this orange curve is not a straight line. So that's it.